Thanks for giving me the opportunity here to speak. So today I'm just going to talk about doing an ensemble common filter for a model that has an adaptive mesh that's non-conservative. I've put a picture of sea ice here because that's our main motivation for this. Really thinking about modeling sea ice with an adaptive mesh to do a better job of capturing things like lead formation, et cetera. So I should say this is joint work with Ali Aidogu and Alberto Carrassi, of course, who you all know, and Chris Jones, as well as Colin Guider and Sue Kuhn, who is also here. So just to motivate, an adaptive moving mesh, these things have been proven to leverage computational power, giving us the ability to model with the same number of grid points, but refocus our resolution in places where there's action happening, where the fun stuff is taking place. So for example, let's see. One of these is a laser. So if we have some turbulence forming, we can increase resolution in some way to try to capture that while sort of leaving the resolution lower where less exciting things are taking place, right, to allow us to better capture those things. This is just an example for geophysical flows. It's also good for pattern formation. Here's a reaction diffusion equation where you can refocus your mesh to help better capture those patterns. Most of these adaptive mesh methods, they conserve the number of nodes, but we don't necessarily have to do that. And as I said, sea ice was one of our main motivations for this. In particular, a sea ice model named NextSim. NextSim uses a triangular mesh. It is also a Lagrangian solver. Let me show you this movie so that you can see some of the remeshing happening. So this is an example of a polynya forming. So here what we have is ice thickness. And what you can see is that due to some wind driving and ocean currents, the ice is diverging away from here. So here you've got zero thickness, so this is open water. And you can see triangles here kind of coming in and out of existence, right, as the mesh adapts. The basic rule for this is that because the nodes here are advecting with the sea ice velocity, sometimes a triangle may have an angle that becomes too small, and nodes get too close together. And that's when we need to do a remeshing. So for example, here, these nodes have violated a condition, a distance condition, and so we remesh. We remove those nodes and make a new triangle and put the values back, the sea ice variables back at the center of that finite element. So it allows for this really nice modeling and formation of these polynyas. And just to show you, let's see. We'll see how my internet's working. This one's a YouTube video, so hopefully it will play. This is SAR data that shows very similar ice motion. So this is coming from the Sentinel-1, but here you see the formation of a polynya. And NextSim is able to really kind of capture that kind of dynamics because of its mesh setup. That's important not only for short-time ice forecasting, say for shipping, but also atmosphere exchange, and sea ice is a layer on top of that. Okay, so one thing that we're really interested in doing with NextSim is data assimilation, of course. Model's never good enough. You always have to do DA, right? So in particular, the ensemble common filter, which you're all familiar with, is one that we would like to use. So I won't belabor, this is just the ensemble common filter. But an EnKF, as useful as they are, is very easy to do, say, with an Eulerian model. With an Eulerian model, you have the same number of grid points. Oops. Oh, there, it's back. You have the same number of grid points or nodes. The dimension of your state vectors for, say, two ensemble members, maybe the ith ensemble member and the jth ensemble member, are the same. All the information is stored in the exact same spot. It's a very straightforward calculation to get your Kalman gain. If you have an adaptive mesh, even if it's conservative, things are not in the same location, but you can further complicate things by having different numbers of nodes. So in particular, for something like NextSim, you may have an ensemble member with n nodes, and oh, that should be an m, I'm sorry, and maybe one with m nodes, but the dimension of those two state vectors will be different, and the nodes will be in different locations. So the question is, how do we address this issue if we want to calculate the ensemble statistics? So one approach that one could take is this idea of a reference mesh. In 2D, this might be a mesh that you choose that gives you only, at most, I should say, at most one node in every grid box. So that would mean some ensemble members will not have a node, say, in that box, but you at least know that you've grouped them in some way. So you may take those ensemble members, maybe you put down this grid, and then if an ensemble member does not have a point in that grid box, you interpolate to it so that you can match the dimension. That's the key here. Then you can do an EnKF on that reference mesh. Then you have to map back somehow, back to the original ensemble member. 2D is always harder than 1D, so we start with 1D. This is what it might look like in 1D. It's the same idea. We have adapting grid points, and then we might decide on some fixed reference mesh that we want to use to compare all of the ensemble members. So in this case, we might just have at most one grid point in an interval. So an experimental setup for this, we'll take two examples. One is Berger's equation, and one is Kiramoto-Shibashinsky. Berger's equation is nice because we have a clear structure, the shock that we want to track. This is something that adaptive meshes are good for. In this case, we'll take just an interval from 0 to L. It'll be periodic. We have some initial condition, of course. And we'll allow the mesh to evolve just with the flow, right? So typically, say for Berger's equation, this is an example of how the mesh will adapt. We've got time on the y-axis, space on the x-axis here. We might start with these initial green points. They'll evolve with the flow. They'll run to where the gradient is the largest, so you can see the shock propagating in time. So as they do that, they'll move together. But that could create a problem. Points may get too close together, right? We don't want them to be at the same place. We might get some singularities. So we have to have some rules that allow us to remesh when either points get too close together or too far apart. So the rules for that in this particular setup are the following. If we have 2 points, say zi and zi plus 1, if they're less than some tolerance, we remove them. So you can see that happening, say, here. Maybe these 2 points are tracking together. They got too close together, and one of them disappeared, right? It could be that 2 points get too far apart. As things, say, run with the shock, we start losing information where we don't have grid points, so we want to insert another one. So we have a condition, another tolerance, where if they're too far apart, we add a point. So you can see that here, these points are moving through. Those got too far apart, and another one was introduced exactly halfway in between. So those are the mesh rules for this particular setup. Once we have this, we would think about how we might want to do the data assimilation step. So we have some initial ensemble. We have our forward model with its adaptive moving mesh. At the time when we get an observation, we'll have a set of ensemble members, all of different dimension with grid points in different spots. So we'll need to do some kind of mapping to our fixed reference mesh. I'll talk about how we define that. But once we're there, we have a forecast that's all lined up, the dimensions matched. So we can do an update. We get an analysis on that reference grid, which we can use to infer information. And then we want to go back. One thing I think that we don't want to do is just evolve from the fixed mesh. That destroys some of the Lagrangian nature of the evolution. We want to go back somehow to the less structured mesh, right? Because this one is sort of at regular intervals. And we want to keep those forecast statistics. OK, so how would we choose the mesh? Well, in this case, the remeshing rules, they're tied to the dynamics, right? So they're driven by the physics. So we want to carefully consider those. So however you define your adaptive mesh, you want to think about that in how you might choose your reference mesh to do this. So we'll make our choices based on those rules, and they give sort of a natural set of choices. One of the rules that we had was that if 2 points were too far apart, we inserted a point between the two. So that means that no points will ever be further apart than delta 2. So what we could do is divide our interval into L over delta 2 separate intervals. And in that case, we know that because of the rule, we'll always have at least 1 point from each ensemble member in one of those intervals. So for example, here I've got a cartoon of 2 ensemble members. In this one, I happen to have 2 from member 2 and only 1 from member 1. Here I've got 1 of each. Here I've got 2 of member 2 again. I think I have more points from member 2, but you get the idea that we'll have at least 1 point from each ensemble member there. That's one choice that we could make. The other choice is to use the other rule, we know that if 2 points ever get further apart, then we remove one. So in that case, we know that each interval will have at most 1 point, right? We'll never get more than one if we chop up the interval this way. So here you can see that, say, for member 2 and member 1, we have both. That's nice. It's good to make a comparison there. We have one in each. But here we're missing one for member 1, so we'll have to account for that somehow. But this is the other choice that we can make. And this is what the reference meshes would look like. You just chop up the interval from 0 to L in regular spacing. OK. So those are the choices for the reference meshes that we can make. How would we actually do the data assimilation? So if we're in the low resolution case, we may have more than 1 point from some ensemble members. So in that case, we'll average those values together. So here's a picture of this. This is maybe kind of hard to see, but here in the dark blue, we've got the forecast on the adaptive mesh, and here is the forecast after we put it on the reference mesh. So the way this could work in the low resolution case, here's our forecast. And let's see, we have more than 1 point coming from the forecast here. So if we want to put this on gamma, sorry, here's the forecast, the dark blue. So here we have 2 points, say, in an interval. This is the fixed reference mesh point, so we average those and place it at that interval. And we do that any place where we have more than 1 point in an interval. Then we can do the update. So here's the analysis on the fixed reference mesh. That would be this one here. So we do the update, this sort of light line. So here you see it's getting updated. Then we have to go back. So what we then do is just take that updated value and we put it back into its previous mesh location. So this point lines up with that one, and that point lines up with that one. And then we can evolve from there. And that may not seem like the best way to do it, but it does work OK. In the high resolution case, it's maybe a little easier to think about. We have a forecast on Z. So here's our forecast. We lay down our reference mesh. So here would be a reference mesh point. We shift that point over to the reference mesh with its value. And we do that with the points that are nearest to that. But maybe we were missing a point. So what we do is we interpolate after the shifting. We interpolate to the reference mesh node to get a value there. Then we can do the update. And then after the update, we put them back on their original grid so that we don't destroy completely the dynamics of how the grids were moving. OK, so let me just show you some of the numerical results from this. So here's for Berger's equation and Kiramoto-Shevchinski. We've got blue is forecast, red is analysis. HR is the high resolution case. The lighter red is the low resolution case, and we have their spreads. This is the observational error. So you can see here the high resolution case, the low resolution case actually outperforms the high resolution case in some places. They both do pretty well after enough time. Which is kind of surprising, thinking how much information you feel like you're losing with the low-resolution case. Here are the results for Kiramoto-Shevchinski. The high-resolution case does a pretty good job. Low-resolution case hovers around observational variance. But more importantly, these are both better than the free runs, right? If it weren't doing that, we're not doing anything right. So that's encouraging. And they do seem to perform pretty well. These are assimilating Lagrangian data. So here we were just taking 10 observations at specific times on a regular grid. But one might think that if we're updating the mesh and the mesh is with the flow, if we had Lagrangian data, say these were buoys or something, we may want to assimilate that as well, really learning something about the flow. This is the case for Berger's equation, where you can see here the Lagrangian data in the darker red and blue. And what's interesting is that even though you tend to have less observations, the assimilating Lagrangian data can outperform assimilating the Eulerian data. Although once you get out here, if you can see, let's see, right, as everything kind of goes to the shock, we get less and less observations, so you start to lose some performance there. OK, so that's with a fixed reference mesh. What we're doing to extend this work is actually thinking about updating the mesh itself, especially if we have Lagrangian data, right, where we really know things are moving. So what does that entail, and why would we want to do that? Well, so in these AMM models, the mesh structure is driven by the physics, right? So if we have physics driving the mesh, maybe we can use observations of the physics to update the mesh. So in particular for sea ice, the velocity is directly tied to the thickness of the ice, the drag, all of these other things that we may be able to measure, concentration especially. So can we use observations of those to influence the actual mesh? Okay. The other question we have to ask is what makes for a good mesh update? I like to think of it this way. If we make an observation of, say, of a flow, we're observing something that is real and that is continuous. Our model, of course, is discretized, though. It's a representation of that. So one might think that if we were to imagine placing our initial mesh, say these green things, and then if we actually had a picture of the flow, we could trace out where they go. I could, let's see, wow, that won't let me draw. So I could say, here's 2 points, and I actually, let's say I know the whole flow. I could follow them, and then I'd say, oh, those two got too far away, so now I'll insert one. I just follow my meshing rules as the flow evolves. And then at some time, I should end up with what that mesh would have been for my model, right? And we could say that's maybe the true mesh, right? But of course, we don't know the flow, right? We don't have it. But we do know that it depends on the physical values. And so we'll just aim to update the mesh based on those physical values and hope that the ensemble statistics of each ensemble member give us what we might say is the best analysis mesh we can get. So how can we do that? Well, the key to doing the EnKF in these cases was really just matching dimension. This is the high resolution case from before, showing sort of how we move things to the fixed reference mesh and then interpolate a point to ones that we're missing. To update the mesh, what we'll do is actually take an augmented state vector. So now we want to think of the grid points in our state vector. If we play this game, we may have some ensemble member. This time what we won't do is shift them, because we care about the positions coming from the ensemble member. So we'll leave them where they are, but we have to match dimension. So what we do is interpolate to any interval in the high resolution case that's missing an ensemble member. And we don't just interpolate to the center. That might bias things. So what we do is we interpolate with a mean at the center and a standard deviation of delta 1/2 with a conditional check that if I actually chose a point outside of the interval I was interested in, I draw again until I'm in that interval. So we sort of randomly place it in that interval and then interpolate the physical value there. And this forms our state vector. Some of these tildes here, these tildes would be interpolated points and interpolated z point. But we fill a state vector that would be twice the size of this one in the high resolution case. OK. So now when we want to do an update, it's a very similar procedure. Instead of a mapping, though, we just match dimension. Instead of a fixed reference mesh, we have an augmented state vector. We can still do the update. Then when we go back, we just want to go back to the old dimension. The procedure is do our forecast, interpolate to the empty cells. We get observations. We have an observation operator that interpolates to wherever the observation is taken. We do the update, so this point moved here, this point moved here. And then we get rid of points that were interpolated to. So we only keep the ones that initially came in the forecast. OK. Let me show you some of the results of this. So here's the high resolution case on the fixed reference mesh. And here's the high resolution HRA, I call it, for the augmented vector. Excuse me. What's interesting to note here is that this is for Berger's equation. And I should say what you're looking at. There are more points than this, but I'm leaving some out so that we can see the spread in these values. So here, the blue circles are the analysis ensemble member at that point. The black circle, I don't know why that's red, but the black circle is the analysis mean. And the little green pluses are the forecast ensemble before updating each ensemble member. So one thing to note is, first of all, for the fixed reference mesh, it may be a little bit difficult to see here, is that everything is just vertical, aligned at the fixed reference mesh. Here in the spread, you see that there's spread in the location and not very much here for the U values. What ends up happening, especially for Berger's equation, is that the forecast in just the first few steps collapses really close to the truth because we're updating both the physical values and the locations. So much so that the spread becomes so small that we stop assimilating a little while after. Let me show you the results of this. So here, this time, instead of the light colors being the low resolution, they're the augmented state vector. And so you can see, and then this is also compared to just the high resolution. So you can see here that there's a little bit, I guess you can't really see that. Maybe I'll use my mouse. Does that show up? It doesn't in this form. But right at the beginning, between 0.5 and 1.5, we're doing a little bit better with the HRA case, but eventually, because the ensembles have collapsed basically to the same solution, we start to drift away, which you can see at the end. Oh, good timing! At the end of this, we really drift away from the solution there at later times. Okay, so that's a little discouraging that things collapse, but maybe what we can just do is resample a little bit, add a little bit of jitter, especially given that it seems in the augmented state case we can get very good updates because we're updating both of these values. So adding some randomicity doesn't necessarily destroy things. So we do the same thing, but then after we do the update, we just add some random noise to the physical values only, not the z values, but just to the physical values. If we do that, this is what we see. So here now I'm adding a little bit of jitter. So before, everything looks very much the same, but then as the shock crosses when we would normally have collapsed our forecast, we add some noise to the u values so that we can then start to track this. And so it's not drifting as much as it otherwise would have. So you can start to see the jitter added in there, as these are much bigger than before. When we do that, we get much better assimilation, so we still do well at the beginning. This is kind of an annoying part. This is when we cross the shock, but then we actually are able to track this really well. And it's pretty robust to the amount of noise that you add. I mean, too little noise, it doesn't do anything, but you can add a lot of noise and still get good results. It doesn't necessarily destroy things very easily because I think the updates are going very well. Here's Kiramoto-Shevchinski. So the collapse of the ensemble to sort of one solution is not so much a problem here because of the chaos. So this is the regular high-resolution case. This is the augmented case. You can see that we just get some noise because of the chaos, and it does a pretty good job. I like looking at this because you can see all of the ensemble members are really aligned. They have different u values, but they're aligned with the Kiramoto curve. So here are the results. Doing this is not adding jitter. So it does okay. It does about as good as the low-resolution case, but it still does collapse quite a bit, and we don't quite have enough spread. You can see the spread here is very low. The light blue would be for the HRA case. This is the HR case, which actually has quite a bit. And part of that actually increased spread is really because we are shifting these values, right? We shift to a fixed reference mesh, then update, then go back to the old mesh. That's sort of an artifact adding a little bit of noise to it as well. But if I just add some jitter again, so now you can really see I'm adding some noise, and it gets amplified by the chaos when I do that. Things still line up on the curve, but we start to get more a spread that looks more like the HR case. And in that case, we can outperform it. So now here we've got the low resolution, sorry, not low resolution. This is the HRA case in light red, and then the high resolution case. And here it's sort of, I've chosen the noise to kind of match the spread we were getting in the HR case. And in that case, we get better updates. So we get some improvement. Okay, so those are just some of the results that we've gotten so far doing this. Just to conclude a little bit, it's really nice that these AMM models allow us to leverage what computational power we have, but focus on the parts of the model that matter. Ensemble methods are desirable DA methods. I guess if you're in the right linearity and nonlinearity regime, that was an interesting talk. Here we've developed some methods, both using a reference mesh to do it, but also using a mesh where we actually update the locations as well as the physical values. We've not done that with the Lagrangian data. That's probably where it's really a good idea to think about how you'd want to update the mesh, but we'll extend that. There's another method, too, that's been used. So projecting on this reference mesh, you can think about moving things around. You're kind of messing with the Lagrangian nature of your dynamics. And some work that Francois had initially done when he was at Nansen was a method where you track these meshes, and then you estimate the covariances using mesh elements that originate from the same area, and that's another avenue that we also want to continue on. Just to show some of the reference mesh work so far with the reference mesh is beginning to make its way into NextSim. So here using SMOS CS thickness data, you can have some forecasts, some increment, and then get a nice looking analysis. So it's starting to be extended up into 2D, where the rules then would be based on your angle conditions instead of just two things too far apart. So with that, I'll just conclude with some of the relevant references and say merci.
Questions or comments? Yep. Could you comment on how the dimension of your analysis and how much that actually is bigger than the dimension of the individual models?
So the dimension of the analysis in the HR case where we go to the reference mesh is just the same as the number of grid points, right? Right. So when we do it, when we're updating things, if it's n, it's 2n. We just have a where we're making a new. Oh, sure, yeah, yeah. So the dimension of the analysis. Oh, compared to each ensemble member. I'm sorry. Yeah. So it'll vary. Some ensemble members they'll range in the number of points they have based on those rules. Typically, I think we'd want to take for the analysis the one where we included those points, so we have something similar to compare. So we don't really, I wouldn't say that we calculate an analysis after we've removed those points. It's just to go back and forecast again. Does that?
Well, I'm just sort of thinking of computational cost. If you're doing
yeah.
analysis on has twice as many points.
Right.
Going back and forward, maybe you could have got away with fixing your number of points on that.
Yeah, this is a really, so if the improvement is marginal, say in 2D, right, and you don't want to double everything and go through, well, I guess you have some interpolation in either case, but yeah, it could be much more computationally inexpensive to use a fixed reference mesh. I think probably in the case of Lagrangian data, where you really had something to track, it might be worth the cost, but that's something that we've got to look into, yeah.
Thank you very much.